So up to this point we've indicated that the slope of a secant line to a function represents the average rate of change of that function over the given interval. The slope of the tangent line represents the instantaneous rate of change. Now just in terms of rates, we know that if we have a positive slope, that means that the quantity we're talking about is increasing as time goes on. If we're talking about a negative slope, then the quantity is decreasing as time goes on. Now in the last video we talked about how to find the slopes of secant and tangent lines, and I want to take that just a little bit further. I have my point P labeled as a comma f of a, and I have my point Q labeled in two different ways. In the last video I talked about the horizontal distance between A and B as being called h, and so we labeled Q as the x-coordinate of the first point A plus the change h, and then the y being f of a plus h. An alternate way to label that point would simply be to call it a different variable, b comma f of b. And so depending on which two of these you use, you can get sort of two different looks to the secant slope equation. They're the same equation, they just look a little bit different. So if I use the a and a plus h formula, I would get f of a plus h minus f of a all over h. If I use my b comma f of b notation, it would simply be f of b minus f of a over b minus a. Now to move towards finding the slope of the tangent line, all we need to do is make h approach 0 or b approach a. And so I can take either of these two limits to come up with my instantaneous rate of change. So I could take the limit as h approaches 0 of f of a plus h minus f of a over h. Or in this form, I could take b approaching a. So limit b approaches a of f of b minus f of a over b minus a. Both of these will represent the instantaneous rate of change of f at x equals a. A symbol that you will see used to represent the slope of the tangent line at x equals a is f prime, which means the slope at what value? X equals a. More about that notation later. So let's take a look at a couple of specific examples of rates of change and apply them to the formulas we're talking about, just to make you a little bit more comfortable with them. Let's suppose we're talking about the number of cases of a disease after a certain number of days t. If you want to know the average rate of change over a certain period, from time 1 to time 2, then again, definition of rate of change is the change in cases of the disease over change in time, which would be the subtraction of number of cases between the days we're talking about over the number of days, t2 minus t1. If I want to talk about the instantaneous rate at which the disease is spreading at time 1, then I simply take the limit as time 2 approaches time 1 of my average rate of change. Instantaneous rate of change, remember, is the limit of the average rate of change. Alternatively, if you wanted to call term 2 term 1 plus h, then you could rewrite the limit above as limit as h approaches 0 of n of t1 plus h minus n of t1 all over h. And the instantaneous rate of change can be notated as n prime at the point we're talking about, in this case t1. Another common rate of change in science is velocity and acceleration. By definition, velocity is the change in a particle's position over the change in time. By position, we just mean where a particle is along a straight line at time t. So is it at the 0 meter mark, the 1 meter mark, etc. Okay? So it's the change in position Alright, so I'm moving into average velocity, which will be change in position with respect to time over an interval. So applying the formula, it's going to be the change in position, subtract the two positions, divided by, subtract the times. And that will be average velocity. To get instantaneous velocity, simply take the limit as time 2 approaches time 1 of the average velocity, and that notation wise would be s prime of t1, which for convenience, since velocity is so important, we will just call that v of time 1. From science, you are familiar with position time graphs, which is what I have here. During this interval, a particle is moving towards the right. If it's moving, it's either moving up and down or left and right. It's moving in the positive direction. If you take a tangent line at this point, what you are getting is the velocity at that point. And a positive slope, a positive velocity, means the particle is moving forward. It's moving right, it's moving up. Okay? If you have a section here and we have a negative slope, which means you have a negative velocity, it means the particle is moving in the negative direction. It's moving backwards, it's moving left. And just as we talk about the fact that velocity can be a positive or negative quantity, speed, by definition, is the absolute value of instantaneous velocity. And so in physics we also talk about acceleration, which by definition is the change in velocity over the change in time. And so average velocity over an interval is simply this change in velocity over the change in time. And so instantaneous velocity is the limit as time 2 approaches time 1 of the average velocity. And this, notation-wise, is v prime of t1, which is equivalent to acceleration at time 1. If acceleration is positive, it means that velocity is increasing. Acceleration is negative, it means velocity is decreasing.